we're going to start by looking at returning feature importance from logistic regression models. You've already done this. We access the model weights by making our logistic regression model. We then fit our model, and then we access this coef attribute. So coef underscore. Remember, this dot implies it's an attribute of this model. It is part of the model object that we've created. Here, we're predicting a single label, whether people survive or whether they don't, or if, for example, maybe we've got, does this person have cancer? Does this person not have cancer? Something like that. In that case, we always take the first element of the coefficient attribute. So that's this 0 here in the square brackets. And the output we get is something like this, a long list of numbers in an array. In this array, we've got one feature per column. So maybe this is age, maybe this is sex, maybe this is fair, and so on and so forth. So we've got one number per the columns that we fed into our model in our X-trained data. Now, the model may predict more than one outcome label. So maybe you've got, is it classifying from these possible species, is this a dog, cat, or a mouse in this image? In which case we would have different weights for different labels, but that's not something you need to worry about right now. But do be aware, if you do a multi-class classification problem, this code will be a little bit different. Now, before we start trying to interpret what each of these numbers mean, let's actually just turn this data into a slightly more readable format that associates the coefficient values with their respective features. So what we've done here, we've grabbed the coefficients like we did on the previous page and saved this into a variable called co_f. We've then created an empty data frame. We create a column called feature. Now this is just taking the names of the features from our X data frame, and that's what we get here, male, P-class, age, etc. It's just taking the column names out of this. Now we can add in the model coefficients to a new column called coef. And again, these, because of the way we are running this, because of the way Python works, these will always be in the right order. As long as we're accessing the same things throughout, they will, we don't need to worry about the fact that male isn't actually going to be this one here, or SIP SP is going to be this one here or something. These are going to be in the right order, and we can just join them up into one data frame. So what we've got here, our coef column, is the model coefficients that we pulled out. And then next, we take the absolute value of the coefficients. So if it's negative, we make it positive. If it's positive, we don't touch it. We leave it as it is. Now this I'll talk about a bit more in a moment, but it just helps us to understand the absolute contribution of the feature to the importance of, or how much it's contributing to the model's predictions, without having to worry about whether it's, making us go, oh, this person's less likely to survive or this person's more likely to survive, which is what the signs here are implying. Finally, we've just sorted by the model data, sorted by the values, the absolute coefficient. So again, this has just allowed us to put the most important, most impactful feature at the top here. So step back a bit. Now we've got a nice data frame of our model coefficients. What does this all actually mean? Well, we standardized our data before we made a logistic regression. So what this means is we can interpret the magnitude of our weights as just basically some indication of how much influence they are having on the model. Larger negative numbers, so very low, kind of, -10, -15, that, the lower you go on the number line, weights with higher negative numbers mean that the feature correlates with, in this case, a reduced chance of survival. So being male here is associated with a reduced chance of survival. The higher positive numbers mean an increased chance of survival. So here, higher fair is associated with an increased chance of survival, but it's not having as much of an impact as being male. Something close to 0, so down here all the way at cabin number, we've got 0.01, negative 0.01. That's having very little impact on the model prediction. The model is practically ignoring that on average across our different people. Another layer of what does this all mean? I'm talking about these numbers and going, well, minus something is quite important and positive this is quite important. But what is this number? What on earth is it actually talking about? all of the values in this table are what's called log odds. Now, log odds are going to crop up a few times throughout the session today, so you don't need to have a perfect understanding of them. You don't need to have a perfect understanding of odds, log odds, probability, but I think it's useful to spend some time understanding what a log odd is and how it relates to probability, etc., because it will come up again in some of the later explainable AI techniques that we talk about. So, before we get to log odds, we need to understand what odds are. Now, odds are just the ratio of the probability of something happening to something not happening. Probability is just a way of sharing how likely something is to happen. So if we have a probability of 1, the thing is certain to happen. There is no question this thing is absolutely going to happen. If we have 0, it's impossible for that thing to take place, that event to occur. If we have a probability of 0.5, there's an equal chance of something happening and not happening. So that's like a fair coin, flipping a fair coin. There's an equal chance of me flipping it and getting heads, and an equal chance of me flipping and getting tails. So odds, as I say, are the probability ratio of the probability of something happening to the probability of something not happening. So I've picked up rollerblading again recently. Terrible idea. Great fun, but, you know, wouldn't recommend. Of every 10 times I go rollerblading at the moment, I fall over 7 times. That means there's a 0.7 probability of me falling over. So probability of event falling over is 0.7. The probability of not falling over is 0.3. Now, how we calculate odds, as I say, is the ratio of something happening to not happening. Effectively, this is P, the probability, over 1 minus P. If we plug in our numbers from up here, so the probability of the event happening, we get P on the top, so 0.7. And then to the bottom, this probability of something not happening is 1 minus the probability of it happening. So we get 0.7 over 0.3. Our odds of me falling over are 2.3 recurring. I've now been practicing lots. I only fall over 2 times out of every 10 times I go rollerblading. Plug in all our new numbers. This time our odds are much lower, 0.25. Now, odds are the ratio of the probability of something happening to not happening. Log odds are just the natural logarithm of the odds. Don't worry too much about what the natural logarithm is in this case, but basically it transforms the number to effectively a slightly different scale. So let's look at what this does to our probabilities, our odds, and our log odds. I fell over, before I skate practice, did lots of skate practice, I fell over 7 times out of 10. My probability of falling over was 0.7. My odds of falling over were 2.333. So that's what's worth noting here is it's positive and it's above 1. The log odds of me falling over after I transform this to this new scale is 0.368. After skate practice, probability of me falling over was 0.2. I only fell over 2 times out of 10. The odds of me falling over are now 0.25. Worth noting that's less than 1. And the log odds of me falling over when I've done this transformation is less than 1. Or less than 0 even, sorry, it's a negative number. So, when something's less likely to occur than to not occur, so the probability is less, sorry, I don't think I've written that right there. Something is less likely to occur than to not occur. Having a moment here. Basically, let's look at our probabilities. So very low probabilities result in, so odds, probabilities of less than 0.5, I'm less likely to fall over than I am to fall over, for example. Then our odds are between 0 and 1. They will be less than 1. And our log odds will be negative. Now start looking at the probabilities, the higher probabilities. Let's assume it's my first time skating and it's extremely likely that I'm going to fall over. The odds of me falling over can become incredibly high very rapidly. And the log odds will always be positive. But they don't go up to quite such a high scale. So you can see here that the odds are up to 9,999. If the probability was even more certain, that number would become bigger, but our log odds have not become so large. Now, log odds versus probability. an odds versus probability here. We've got our odds on the y-axis and our probability on the x-axis. As our probability increases and gets closer and closer to 1, closer to being absolutely certain that the event is going to occur, you can see our odds are exponentially increasing. Meanwhile, we've got the same probabilities across our x-axis here, but the log odds have got this nice relationship of being bounded more or less between roughly -4 and 4, and we have this lovely feature of it where the probability is 0.5, whether the event is equally likely to happen as not happen, then it is centered around a log odds of 0, and anything where it's less likely to happen than happen is negative. Anything where it's more likely to happen than not happen is positive. So don't worry if that didn't all make sense, but hopefully it will start to help understand what these numbers and give you a little bit of a sense of what these numbers mean. We're returning to our table of coefficients. Remember, these are log odds. On the unscaled data, these coefficients are representing the change in the log odds of the outcome occurring for a 1 unit increase in the corresponding feature. So assuming, let's ignore the fact that we scaled our data for a logistic regression model. Let's assume we didn't. What this would mean is that for every 1 unit change in age, let's assume that that's a 1 year increase in age, then your probability of survival, your log odds of survival would decrease by this much. $1 higher fare, for example, your log odds would decrease by, we haven't got fare on here, but male, for example, so being male would decrease your log odds of survival by 1.36. The key things to take away from this are values less than 0, mean a 1 unit change in this feature makes the outcome less likely to happen. So you're less likely to survive if you're male. It's below 0. Values greater than 0 mean a 1 unit change in this feature makes the outcome more likely. And the bigger the number, either direction, the stronger the impact of the feature on the predicted outcome. We take the absolute to make it possible to rank the features by their impact, regardless of the direction of the impact. So now we know that each of these values are log odds, and on unscaled data, they'd represent the change in the log odds for a 1 unit increase, so being 1 year older, $1 higher fare, for example, in the corresponding feature, assuming that nothing else has changed. But we scaled our data. So what happens here is the coefficients are the change in log odds for 1 standard deviation increase in the feature. Now, what's 1 standard deviation? In a normally distributed set of data, one standard deviation would be, sorry, having another moment here. So let's assume that we've got a normally distributed set of data. We've got, let's say, the height of people. Let's assume most people are around about 180 centimeters tall, and we get some people that are more than that and some people that are less than that. But in general, it's centered around that maximum peak where most people are around that sort of height, and then it drifts off to either side like we're seeing in this bell curve here. Now, what this means is that about 1/3 of people will be in this kind of section here, quite close to the average. And about 1/3 will be quite in this section here, a little bit less than average. So these people are a little bit more than average. These people here are a little bit less than average. But in a normally distributed set of data, it's about 1/3. 2/3 of people in total will be within this section. And nearly all of your data will be within 3 standard deviations of the mean in either direction. Now, looking at age and fare in our data set. So we've got a histogram of the age in the training set, and we've got a histogram of fare in our training set. You can see these aren't perfectly normally distributed. This one in particular, fare, is quite skewed off to one side. And the histogram of the age in the training set is a little bit more centered around this, but we've still got not a perfect situation. Now, remember, we standardized our data. So what the values actually look like are this. When we've plugged in our data to our data sets, our fares are sitting around about 0 or somewhere to about -1, -2, and actually up to 1, 2, 3. Now, map this to the real values, map this back to the real values of our data. So this is what we've plugged into the data set. This is what we've plugged into, this is actually what our data looks like behind the scenes. In this case, the mean age is around about 29.5 and the standard deviation is about 12.99, about 13, let's say. What this means effectively is that for an increase in age of 13 years, 1 standard deviation in our actual data set, the log odds of survival decreased by about 0.5. For fair, the mean is about 32.14. This red line here, this solid red line, each dotted red line is indicating 1 standard deviation from the mean. So for a $51 increase in fare this time, so $51 is the standard deviation, the log odds of surviving increase by 0.27. The reason I'm having to tell you all about the standard deviations, etc., is because we have standardized the data, it no longer correlates to a 1 unit increase. We're not saying that for $1 increase in fare, the log odds of survival increase by this much. If we've pulled out the code of the data set of the tables using this method on something we've standardized, it's really important to remember that it's 1 standard deviation, not 1 unit. We can also convert the log odds that are outputted by default to odds. We take the exponent, that's the mathematical opposite of taking the log in this case. And we can also convert the log odds to a probability if we want to as well. And this will then all tell us the change in probability. Now, all of this comes with a lot of assumptions and potential issues, up to and including the fact that I may have taken the wrong log for some of these examples, as people have just very validly pointed out in the chat. So you can see it's very easy to start tripping up and quite difficult to explain to your potential stakeholders. It relies on there not being correlated variables in your data set as well. So actually, for example, let's say that you've got cars in your data set. As cars get older, they also tend to have been driven further. It's not always the case, but it's quite commonly the case. So it relies on there not being correlated variables like this in your data set. Maybe there's a medical measure that you always find changes as people get older. They always, there's always this correlated relationship between the two. The change in probability isn't consistent. It can be influenced by other variables. It's not the most accurate option for continuous variables. There's a lot of limitations of this approach. So should you use feature importance in logistic regression to actually try and tease out these details? It's up to you. For now, feature importance, as shown by the log odds, can at least give you an idea of which features tend to have the biggest impact on the model's predictions. That hasn't changed, that's still true, and which direction this impact is in. Is it associated with an increase or a decrease in the predicted outcome? I think we could all do with 5 minutes. So let's take a quick coffee break. We'll stretch our legs 5 minutes, and then we'll return to talk about feature importance in logistic regression. Sorry, no, we won't. We'll return to talk about the tree-based models, which you will be pleased to know are far nicer, far easier to interpret, and easier to create and run as well. Hi everyone. Right, I'll just give it a moment because I know it's only a fairly short break and people's kettles may still be boiling. But just to address a few questions have come up so far. So I will have to come back to a couple of them just to clarify afterwards. But couple of quick ones to address. That using list X on the array of data. If I jump back to where we were for that one. Here we are. So using list X to get the feature names from X and add them as a column. I think this may actually be because this is something like a named NumPy array, not a data frame. In this particular instance, there is some code later on that explains how to get column names out of a pandas data frame. So do check the output of what list X is. The way that I will show you later will consistently work with data frames, so you can be more confident in that. I think there are some mistakes in the code where we talk about the log odds. I will come back and correct the slides and provide some fixed slides because of that. But effectively, fundamentally, what we're talking about with log odds and odds doesn't change. There are, log odds are used in a lot of the things we see today, and the features of them of being positive when the probability is above equal, when something's more likely to happen than not, and being negative when it is less likely to happen than to happen. That is very useful and is something that, is just worth being aware of as we continue through today's session. So now on